Hello everyone, and welcome back to another GIS Mathematics lecture video. And in this lecture video, I want to walk through sort of the key ideas of solving for this inverse matrix. All right, and so to sort of remind everybody where we are here, all right, we have this idea that A times A inverse is going to give us the identity matrix for whatever size A is. I want to make a quick note here that A must be square. Right, and we've brought up this idea of a square matrix before. It just means that it has to have the same number of rows as columns. Okay, so this is our sort of golden equation here, that we have a matrix times its inverse giving us the identity matrix. So basically what we're going to do to approach these problems is we're going to do three things. The first thing we're going to do is we're going to augment right, A and I. Right, so we're going to get a matrix that has A and it has I. I'm going to make a note here that this is not multiplication. Right, we are not multiplying A and I, we are augmenting, which means sticking those two matrices together. Okay? So the next thing that we're going to do once we augment them is we're going to put right A augmented with I into reduced row echelon form. Okay? This is where the magic happens. Again, I'm not going to prove to you why this works because I don't even know how to prove it. But basically, when we put AI into reduced row echelon form, something magical happens. And what we end up with after we do that is an augmented matrix where the first part of the matrix is actually our identity matrix. And the second part is our inverse matrix. Okay? So this step right here is magic. Putting AI into reduced row echelon form magically gives us I augmented with our inverse matrix. Okay? And so what I want to do in this video is walk through a couple of, I don't want to say, one of them is a shortcut and the other one is a way of determining whether or not a matrix is invertible. Because that's something else that we need to be aware of, is that not all square matrices are invertible. Right, we'll find cases where we don't get IA. Instead, this is something else. Okay? So, again, to recap, we're going to augment A with I. We're going to put AI into reduced row echelon form. And then through the magic of matrices, we're going to pull out this identity matrix times, or I shouldn't say times, sorry, this identity matrix augmented with our inverted matrix. And again, notice the order here. A is in front of I. Reduced row echelon form, I is now in front of A. Okay? This change in order is important. So what I want to do is I want to go through a couple of quick notes, and then in the next video, the next required video, we'll go through some examples. So the first thing I want to talk about is the 2x2 inverse theorem. Right, the 2x2 inverse theorem. There's a separate optional video where I actually go through and I prove that this works. I go through the steps we outlined above. I augment the matrices, I put it into reduced row echelon form, and I prove that this works. But if you don't really care, that's understandable. You don't have to watch that video. But what we end up doing is we prove that for a 2x2 matrix, right, for A equals a 2x2 matrix, right, there's an equation we can use to get the inverse. And that equation is 1 over AD minus BC times the matrix DA negative C negative B. Or I'm sorry, negative B negative C. Let me erase that. The matrix is supposed to be D negative B negative C A. Right, where A equals A, B, C, D. Right, this is the 2x2 inverse theorem. So if we have a 2x2 matrix, we can plug A, B, C, and D into this equation to get the scalar, move things around, do the multiplication, and we can get the inverse. Right, and this actually brings up the first instance where we would not have an inverse, right? Because if AD minus BC is equal to 0, right, this does not work. Right, so if we have a 2x2 matrix, we simply use this equation, right? This is an equation. I recommend writing it down somewhere, storing it somewhere, so when you go through the homeworks and the exam, right, if you see a 2x2 matrix, you can bang it out really quick. And again, if you're interested in the proof, there's a separate optional video where I actually go through the process outlined above to come up with this. Anyway, so this is the 2x2 inverse theorem. Remember this equation. The other thing that can happen is a matrix may not be invertible. Right, a matrix may not be invertible. And we talked about this just a minute ago, right, when we said that, if we have the augmented matrix A and the identity matrix, right, if we put that into reduced row echelon form, right, we should get I augmented with A inverse. Right, this is invertible. Right, there will be cases where you will have A augmented with I, right, but you put it into reduced row echelon form and you end up with something that is not I. We'll call it B. Indexed with, we'll call it X. All right, this is not invertible. What I'm trying to get here is this must be I. If this doesn't make sense now, we're going to go through some examples and hopefully it will. So again, I just wanted to walk through this idea that we have two sort of litmus tests. If we get to the point where reduced row echelon form is not I, we stop because we can't go any farther. And if we have a 2 by 2 matrix, right, we can plug it into this equation, and assuming that AD minus BC is not 0, right, we can get our inverse that way. Otherwise, again, we augment A and I, we convert to reduced row echelon form, and then if we get I augmented with something, right, that something is going to be our inverse, and they have to be square. So hopefully that makes sense, and if you have any questions, please reach out. Thank you.